Welcome back, those of you who have been here all day for Science and Innovation Day. Also, hello to our YouTube viewers and to all the new people who is here for the Good Tech Conference. We are looking forward now to a great evening together. We will start off here with a couple of great keynote speakers, right? And then we will have evening together, get together. And, well, I don't know about you, but it sounds great to have a harvest feast buffet together and a great laugh thanks to our amazing stand-up comedian Elin Almen. So this will be an amazing evening in so many ways. The theme for Science and Innovation Day is, as you can see here, co-creation, transformation, but it's also artificial intelligence, which works very well with the Good Tech Conference theme, which is intelligence for this year. So now we are co-creating together from these different kinds of perspectives. For newcomers, we are using menti.com to help us so we can actually co-create in the conversations as well. So you just enter menti.com and you use the code that you see on the screen over there. So whilst our keynote speakers are talking, you can actually text your questions. So when they're done, I will ask them the different questions that you have sent into Menti. So please use that as much as you want, and we will try to cover as many questions as possible. Okay, more details about the evening I will give to you later on, but let's move on to our first keynote speaker. Bioprinting is an additive manufacturing process where biomaterials such as cells and growth factors are combined to create tissue-like structures that imitate natural tissues, for example, skin. Our next speaker got hooked on bio
today, and I'm super happy to be in Sundsvall, and I'm super happy to spread the word about 3D bioprinting. And I'm Nordic Sales Director at CELLINK, and I have been with CELLINK for quite a while, almost since the start. So I've been seeing the transformation from nothing to where we are today, basically. And I will try to take you with me on this journey to show you what has been done and where we are today, and also where the future is. So starting off, we saw a big possibility, because there's a big risk out there with drugs getting stuck in clinical trials. And it takes way too much time, and lives are going lost during this development phase. So looking at this, there's also a cost factor. So time is money, and the cost for a development of a drug is huge. So if researchers can get more accurate data on an earlier stage, this cost can be reduced. And that's what we believe in. And at CELLINK, we always say that if you should fail, you should always fail as early as possible. Therefore, CELLINK developed a bioink to get 3D cell cultures. So this bioink provides the cells the 3D environment. And CELLINK is actually the first company in the world to commercialize this kind of bioink. This bioink is made from different materials, and I will show you during this presentation what kind of materials that can be used. And the main reason is to get the cells to behave like the native environment. The first bioink worked perfectly for mesenchymal stem cells and chondrocytes, but there is no general bioink, and that was something that we received from the market, basically, from researchers. So we started looking at how can we develop tissue-specific bioinks. That has led us to where we are today. So until today, we have more than 50 different bioinks, and we are continuously developing this further, because we will never stop with thriving. So how do we do when we develop bioinks? We look at the first step of selection of biomaterial. So here you can have different components depending on the time frame of the study, basically. So you can have synthetic polymer, natural polymer, or ECM. Then you look at a lot of different components, such as printing fidelity and making sure that the cells feel good. Our main parameters are, of course, printability and cell interactions. Because if the material is not printable, we don't have a business model that holds up. And if the cells are not good, then we won't have happy customers. This is just one example from a partner of ours that was developing their own bioink. And you can easily see that the increase of alginate across the lines makes it more printable. And this is not only to get finer lines, but you can also create more advanced structures, such as an ear or sheep meniscus on the pictures. And they also stay over time, so it's a stable material as well. Developing further, we looked at how can we make this even more in vivo-like. One approach is to actually take ECM. So here we have taken animal-derived ECM. And the ECM provides the cells with the most important molecules beyond structure and biochemical support, and everything to create the in vivo-like structure. The other approach is to develop tissue-specific bioinks by taking specific proteins from different tissues. So for example, this can be more attractive to researchers that aim for clinical trials, because this is more defined than actual ECM. When you take a specific protein, you know exactly what is in there. If you take an ECM, the full ECM from a tissue, you don't know what you have. But as you have understand now, we are focused on bioinks. And that's what we started with. We started with one bioink only, that the founders opened up a web shop. They put up the bioink. They sold out the first day. Great, but there's a limited market. So the founders looked at the market and realized that there's a limited market for bioinks because the bioprinters were super expensive. They cost, as you can see, up to $200,000 and more. So the way to go was to democratize 3D bioprinting, both because then we get a bigger market for bioinks, but also because we never know where the next innovation will come from. It might come from a completely anonymous country. So they decided to start manufacturing 3D bioprinters. And this was going to be super easy to use, user-friendly, and cost 1/10 of the price that were for the existing instruments. So they launched this system that you can see on the picture for $4,999 US, simply so that professors could buy with a credit card on the spot. And this led to quick deals and upscaling, basically. So what CELLINK is good at is taking in customer feedback and market feedback in general. And this led to a third generation, that is the BioX, and this has been the revolution for tissue engineers, cell biology, or regenerative medicine researchers. And I have a short video that explains it, and this is like no other system, basically. it doesn't only look simple, it is that simple. And I believe that anyone can print within 10 minutes. That's how easy it is. And if you don't believe me, I will more than host you in Gothenburg, and I will show you how it's done. And one of the functions that was mostly desired was the modular system, that you can print anything on one system instead of buying 4 different systems for 4 different materials. So we developed a modular system that you can print anything from water to polymers, basically. And this is not only meant to be a promotional video, but another reason behind the success of CELLINK is that we're such a diverse company. We have more than 27 nationalities, and this was made quite a while ago, so I guess we're more even now. And we're spread out over the world, and we actually believe more in hiring talents than filling up open positions. And that's one of the biggest reasons we're where we are. And talking about where we are. So until today, we have reached more than 700 labs. So the technology is not new. Yes, it's new, but it's widely used. We are more than 160 employees. Back in a year ago, we were 50, 60 employees. We're spread out over the world in Boston, Blacksburg, Gothenburg, Kyoto, Stuttgart, and Freiburg. And we have the technology in more than 60 countries already. And this is even though we started in 2016. And I love this slide because it talks for itself, but also because it's such a proof that 3D bioprinting was boring and no one did it. And CELLINK actually achieved on making 3D bioprinting a little bit sexy, because nowadays there's a huge increase of publications in the field. And we're so happy to see this, because that shows that we have actually managed to democratize this. And a few of the users or partners' publications are that we have a partner in Newcastle that was working on printing a cornea, and the organ donor shortage for corneas are insane. Also because the vision impairment treatments are causing this to be even more and more victims, or so to say. So they are actually aiming for clinical trials within 2 years. It's soon. Another partner in Plymouth are working on skin. And I will dig deeper into this soon as well, because this is one of the applications we are focusing on at CELLINK as well. But they are focusing on developing skin for testing cosmetic products. But there's also a huge market for burn victims. And that's why this technology is needed. And I guess some of you saw the news from Israel when they printed the heart, a miniature heart. This was actually a partner that was before that. And there's so much done that the news can't keep up, basically. And moving into the applications that CELLINK has been selected to focus on. So starting off, CELLINK started with one bioink, as I said. This is a study done by that, or with that bioink. So the partner decided to take the human azochondrocytes, mix that inside the bioink together with cell culture media, because the cell culture media are what provides the cells with the nutrients. And the bioink is supposed to give the 3D environment. Then you need a blueprint. And a blueprint is what provides the machine with a pattern, where to extrude and how to build up the model that you want. Then you print it out, you cultivate, and then it's done. We don't only want to print out and then make sure that everything is fine. We want to make sure that it's actually successful. So you can do that with a simple live dead staining. And what is mostly important here is that from day one, you can see that the cells are homogeneously distributed inside the construct. And then over time, they start to making these clusters that they actually should. And then you can see cells per scaffold, that's increasing from 14 to 28 states. So they are also proliferating, which is great. But we're not happy with that because we want to see more. So we want to make sure that they are actually producing what they should. So here we stain for glycosaminoglycans, and you can see that they are increasing over time as well. So that's good, but it also gives a really nice expression of collagen, which makes it a really nice model. Next area is skin. And as I said, this is really hot on all kinds of markets. And it's perfect because skin is built layer by layer, and that's how a 3D printer works. So we wanted to focus on the dermis, and I will show you on this slide. So we have different cells and different concentration of cells to mimic the different layers of dermis. Once again, you need the blueprint. You take the bioink together with the cells. And for the papillary dermis, we have a high concentration of fibroblast. For reticular dermis, we have a low concentration of fibroblasts, and then we have keratinocytes on top. We print those in well plates, culture them for 2 days, then we flip them into the inserts, simply because we want to expose them to the air-liquid interface, to be more in vivo-like. We want to make sure, once again, that the cells are proliferating and creating what they should. But most importantly, you can see from day 5 to day 14 that the cells, or especially in this case fibroblasts, are starting to create the networks that they should. And also the keratinocytes are homogeneously distributed, and then they start to create these clusters that they should. Next application is a proof of concept we did with a pharma company. And they simply took primary cells from patients, and then they tried to culture them, but they didn't survive for more than 2 days because primary cells are a mess. And they wanted to see if they can survive longer in a 3D cell culture. And they simply did. They were surviving for 2 weeks, and then we ended the experiment, but the cells were still surviving for up to 6 weeks. And most importantly, they are having the morphology as they should, and they start to making these clusters once again. I mean, now I'm showing initial data. This is still early phase. There's more needed, and there's more coming, but it's really good start. And another case was, I don't know if you can see, but I hope so. This is printed iPSC-derived cardiomyocytes. They were not beating post-printing, but after printing, they actually started beating. And what is most amazing is the second video on the right, because then you can see that they are synchronized. So they are actually starting to communicate as well, which is quite cool. So we can print cells, we can create scaffolds, we can create tissue-like models, we can create a lot of things, but there is a challenge, and the challenge is that when you create bigger structures, you struggle with diffusion of oxygen and nutrients, so you need vasculature, and the vasculature is a big step. There's different approaches, but one is to create a simple way of vasculature, basically. So we worked on a product because it was, once again, professors came and said, we need this. I said, yeah, okay, we'll take a look. And here's a short video that will explain further. again, for those who didn't understand, those green dots, that's cells flowing. It's so cool. And this is just the start. And we have developed a lot of different techniques and products. But combining all this, there's so much possibilities. I mean, as soon as I meet cancer researchers today, they say that they are doing so amazing stuff, and they are, for sure. But there's so much more that can be done. Just when I mentioned that we can study cell-cell interactions, 90% of the researchers don't believe me. And here we can actually see cell-cell interactions together with any kind of cell flowing inside and see how they start to migrate. It's insane. And one more insane thing is this. This is a partner that was featured on Science Cover recently. So they printed the smallest part of a lung, the alveola, and they could actually show how they could oxygenize deoxygenated blood with this technique. So inside here, you don't have, or you have oxygenated blood. Outside, you don't have oxygenated blood. And this oxygen could actually diffuse out to the outer layer. And this is a big step. And this is going to push the field even more forward. And with that, I am happy to receive your questions.
Thank you, Daniel. I'm so inspired. I feel like I'm also very enthusiastic when it comes to cells right now. I don't know. They are beautiful.
We're looking for talent.
Yeah. Please have a seat. Okay, we have a few questions here, and one of them came in quite early. Perhaps they got the answer as you were talking, but we can still cover that one. What is ECM?
ECM is extracellular matrix. It's a protein, basically, in the body. It's a natural thing.
Where did your journey in all this start?
So I was working in sales in a distributor company, and then I was approached by a recruiter, and then I met two of the founders, and I simply said yes to joining.
Great. What convinced you? Did they have these nice pictures then as well, or?
They told me what they were doing and what the products could do, and I didn't believe them. But when I saw it, I was like, yeah, this is something I need to do.
Obviously, you have been growing as a company, and one of the questions from the audience is, how many researchers do you have in your company?
Good question. So, we have different kind of researchers. So we have R&D for software, hardware, and bioinks. But I would say most of the research is in the bioink department. So that's roughly 20 people.
Yeah. And we talked about it earlier today about co-creation. How important it is actually for you to work with people outside of your company?
Super important, because we never develop a product without a collaborator. As soon as we are approached by a professor or customer or partner that want us to do something, we always check with other users, and then we co-create together with the user. Because we will never be the ones having the answers for everything, and our users won't be the ones that have answers for everything. So together we can make amazing things.
You talked about that you had a great diversity, and you have people from all over the world helping you in doing what you're doing. How do you find those people, or how do they find you?
That's actually a luxury. I mean, we have got quite a good spread of media, so we're quite well known in the field, and we have a lot of applicants for different work positions, but then we meet a lot of people. As I am out traveling now, so I might meet someone talented. But that's how we discover.
Another question is about what is the most challenging issues in your application?
That is a tough one.
Yeah.
Super tough one. I would say the most challenging is to get more people on board, because we know what we are aiming for, and we know that we have a lot of partners that are joining us on this journey, But looking at something completely new, it's hard to get everyone on board.
And I'm thinking about all this. This is what you're doing is you're creating things that we normally have naturally as humans, and now you're creating it through printing. Do you have any like ethical obstacles in what you're doing?
Yeah, I mean, the first day I joined, I asked our chief scientific officer, what can be done? What can we print? And the answer was basically anything. It's possible, but there's a lot of ethical rules and things that we need to follow, and you need to have FDA or CE certified materials and everything. So there's a long process of going through all those steps, but never give up.
Yeah. Do you get help? I mean, how do you get that kind of knowledge to your business as well, if this is one of the obstacles for you to actually move forward?
Together with the bright minds of researchers, because they have been through that journey, they can support us on it.
You said when you started your speech that, well, in the beginning, they found out that, well, this is a great possibility to do this. How do you know that you come up with a sort of a great solution or a great possibility?
I have actually asked the same question, and the answer was, yeah, I've been lucky, but I don't think so. I think when you are a visionary that you can see that this is going to be something big, you have a feeling and you follow that feeling. Political answer.
Political answer. Well, I guess it's not that easy to answer either. So, we have one more question about the future here. When do you think we can go to organ shop and buy new eye or heart? Would it be in close future?
Depending on what tissue, I would say. I mean, for corneas, they are aiming for clinical trials within 2 years. And that's also an external organ, such as skin. So those two tissues might be close in the future. I can say something like within 5 years, maybe. Other more complex tissues are quite far ahead, but still, within research, it takes time.
You said also during your speech that you were able to make this sexy. I guess that could be a challenge sometimes with research, no offense now. I mean, you have a great idea, you develop something great, but then how do you communicate it? How do you make it sexy? Do you have the answer to that?
I would say it's about commercialization, having an eye for what people want, even though they don't realize what they want. I mean, for example, Tom Ford was asking the market, what do you want? And they said, faster donkeys. That's not what they actually wanted, apparently. There's about having an eye for it.
This morning, we also talked about the change of business models. And we saw actually a transformation here. What is your business model?
The business model is to get as many systems out there, to get as many researchers working on this technique, and then working with those users together, because we don't believe in just supplying a hardware or bioink, because we actually believe that a researcher's success is our success.
Yeah. What about the money? How do you get the money to all this? I mean, I realize this is not done sort of afternoon coffee break or something.
I mean, as I was touching base on before, what we want to actually sell is the bioinks. All of these kind of businesses is about consumables. The hardware is a way to get consumables out there.
Okay, another question about like future possibilities. Would it be possible not just to print body tissues, but perhaps medicine as well in the future?
Really good question. There is actually companies that want to print special tablets, so printing pills, because nowadays you overdose or take too small dose. So if you can personalize the pills or drugs, that's a huge step. So it's ongoing as well.
Exciting. Now a question, I think this has to do with the ethics that we mentioned somehow, and also the regulations, of course. What is the source of human cells, and how can you upscale human projects?
Different from different tissues. I mean, you can take fat cells and then you can make them to iPS cells. There's donors. That's up to the researchers that use our technology, more or less.
Okay. Well, you went on board on this project a few years ago, and I can see your enthusiasm is on a high level. If you just sort of look at 10, 20 years from now, where will we be when it comes to 3D bioprinting?
I hope that we have started printing skin for burn victims, because that's something that is needed urgently. That's what I really want to see. Of course, I want to see more tissues being implanted as well, but skin is what I think can actually happen within that time frame.
Thank you so much. I will also give you a gift for being with us today. And I know you're staying for the evening as well.
Yes.
Yes, so at Get Together, please catch him and ask him more about all these things. Here's a gift from the Sundsvall region. You have some cozy time now during autumn.
Thank you very much.
Enjoy it.
Thank you very much.
And our final speaker today, she's a self-taught data scientist, an entrepreneur with engineering background. With a passion to apply artificial intelligence and machine learning capabilities on biomedical science to accelerate the development of new technologies. She does make AI simple and a tool for ordinary everyday issues. And also, at the same time, with a passion, she applies her knowledge into human challenges, such as cancer. A big welcome to Norah, Klintberg, Sakal. Welcome.
Technologic. Buy it, use it, break it, fix it, crash it, change it, melt, upgrade it, chart it, point it, zoom it, press it, snap it, work it, quick erase it, write it, cut it, paste it, save it.
Oh wow, thank you for having me. I'm so glad to be here. Hi, let's talk some AI, let's talk some deep learning. So, AI for you fill the blank. Just as you mentioned, my name is Norah, and I'm self-taught when it comes to programming. I have a background in biotechnology and bioengineering, but I'm self-taught when it comes to data science. And I'm raised in Sweden, in Stockholm, but I'm currently in San Francisco. We've been living there for 3 years, and now we're in New York as well. So I flew in yesterday, so I'm super excited. And currently, I'm bootstrapping my own startup, where I'm building a deep learning platform for cancer and stem cells researchers. So basically, I'm training deep learning models that will help them understand how their cancer cells are communicating, but also evaluate how well their drugs are working on different experiments, basically. And if there's something I want you to remember me by is that I love AI and I love deep learning. I'm applying that on everything. And by everything, I really mean everything. We're going to look at 4 different practical AI implementations here today, starting with makeup. And it's divided into these 4 ideas, but it's also going to talk a bit about the data and the most exciting part, in my opinion, which is training the model and actually see what the model will see during the training and afterwards. So the question for this part is, what do you do when you don't have any data? Then we're going to talk a bit about gardening and AI. The question for this part is, can a simple algorithm still solve like time-consuming and important problems? The third idea is AI in furniture. And I want to ask you, how creative can an algorithm actually become? And the last part, which is, my main focus is AI in cancer. And the question is, can you train an algorithm for cancer cells with cats and dogs? So let's start with makeup. What about AI and makeup? What's the connection between those two? So the problem is that I spend a lot of time in front of the mirror every morning because I enjoy looking like this. And I guess there's other people feeling the same thing. But because of that, I'm also looking for inspirational videos or like tutorials for makeup. The only problem is that if you search for makeup tutorials, you'll get over 30 million videos. And the beauty industry being like a $4 billion industry just indicates that it plays a significant part of people's lives. So I spend a lot of time in front of the mirror. There's 30 million videos out there. But how do I know which one of these videos will actually show me a tutorial that matches my facial features or my particular like unique facial features? And when I thought of this, I immediately knew that you can solve this using AI. So that's the first idea, AI and makeup. But what about the data? So first of all, I started to research this field. I'm dividing this into 3 steps again. First, doing some research, then deciding on the goal. What do you want to train? What do you want the model to do? And the last step is to how to find that data, how to build your own data set if you don't have any data to start with. So the first part is the research. So since it's makeup, I started to research facial features, and you have a lot of them. You have a nose, chins, eyebrows, a mouth. But the most striking and time-consuming in terms of putting on makeup is the eye section. And I started to looking for patterns within these videos, and I saw that the eye shape is coming up a lot. So I started to focus on that. So I narrowed down the problem a bit more and focusing on the eye section and the eyes in particular. And digging even further, I found out that there's 4 different eye shapes out there. There's round, monolid, hooded, and almond shaped. And there's a lot of varieties to those, but those 4 are the most distinct ones, and you can have narrow, wide set, but these 4 are like the ground up. So that's for the research. What about the goal? Since I want to like replace myself with AI, I decided to have photos as the input. So feeding photos to an artificial intelligence network and having it tell me what kind of eye shape I'm having. So just the scope, my eyes, and it's supposed to tell me what shape I'm having so I can navigate through all of these 30 million videos that's out there. That's the goal with this algorithm. But what about the data? Since this was my very first algorithm, I had no prior knowledge and no sources for this, especially not people's eyes. And this is something I really want to stress. There's a lot of open data out there that you might think is not that suitable for your particular problem, but you can use your knowledge and your own expertise and transform that data into something that's going to be useful for you in your application. So that's what I found. I found an open data set with hundreds of thousands of images of celebrities. And what can you do with that? I manually cropped them and divided them into these 4 different categories that I found. And basically, for the folders, for each image, I identified which category it belonged to and just divided it into the right folder of choice. And these are just abbreviations for the different categories, like round eyes, almond eyes, hooded eyes, and monolid eyes. And this is the last one over here. So the final data consists of 4 different folders. And I did this manually because I had no prior knowledge, but I manually cropped out 300 images for each category and divided them into these 4 folders. But what about the training? This is the most exciting part, training the algorithm and see what it actually comes up with or what it actually can learn. So let's look at how to train the model itself. So here's a platform that I built. It's super easy. It consists of 4 different models that you can train. The only thing you need to do is upload the data that you want to use for each class. Like in this case, I have 4 different eyes. I'm going to upload 4 different folders to the network. decide on a project name, and then just start. Let the training begin. So while it's training over here, let's see what the network actually will see while it's training and starting to understand makeup. So back to the aim. We want to feed these images to a network, and we want it to tell us what category it belongs to. So we want to go for a high-dimensional image to discrete categories. The problem with this is that when you go from a high-dimensional image, it's difficult for a network to find the underlying patterns, because images can be expressed as a huge matrix with all of its pixel values. Just like this, it's just a subset of them. So what we need to do while we're training this model is to go from this high-dimensional image into a lower dimensional representation of the same image before we can go into the discrete categories like this. So this is a low dimensional representation of that input image. And this is what the network will need to learn how to decide which category this ice belongs to. And then finally, these discrete categories. But what about the training itself? This is a convolutional neural network. It's a very, very simple one. It consists of these 5 building blocks. It's pretty old, but it's very efficient, and this is the first one that I use for training this kind of data sets. So these 5 different blocks with convolutional operations and one simple top that will actually tell you which category this ice belongs to. And what we're going to do throughout the training, we're going to transform this high-dimensional image into these low-dimensional representations all the way down for each building block, all the way down to this very low resolution image. And then it's going to guess, are these round or not? And this is how it's going to look like inside of the network. So this is actually what the network will see during the training. And we're going to run this hundreds of times until it actually learns. So here it still doesn't know the right answer. So we're going to run it again and again and 100 more times until it actually learns what to do. And now I got it right. And I think the training is done as well. So let's look at that. This is how it looks like when you want to try and find your own shape. And you will quickly find out that I have round eyes, and this is the kind of makeup that will suit my particular facial features. So let's go back to the presentation again. That's makeup in AI, and with the key takeaway, right? What do you do if you don't have data? You use open data sets, and you transform that into something that's convenient for you, that's going to suit your particular feature or your particular case. But what about gardening in AI? What's the connection there? So gardening, my husband and I used to have a gardening company back here in Sweden. We had a couple of employees, so I worked out a lot. And I met a lot of customers, and I spent a lot of time in different gardens. And basically, this is how my phone looked like after meeting with all those customers. So I spent a lot of hours there just looking at their gardens and trying to write like a pricing quote for them. The only problem is that there's a lot of time. First, you have to understand what you need, what services the customer needs, and then you have to write this pricing quote. So I immediately thought again, this is solvable using AI, of course. But how could you do that? So some more research into this field as well. A garden is pretty different from makeup because it consists of many different kind of like environmental categories, like a lawn, you have garden tiles, you have a bush, you have trees, you have a bush bed, flower bed. So for research, I just took all of our most popular services and looked back at all of our different quotes and created a data set out of this. So the goal for this algorithm was to take a photo, give it to a network, and having the network writing the pricing quote for me and then sending it to the customer. So I was just bringing myself out of that equation all along. And this one is pretty similar. We're taking a photo, giving it to a network, and having it writing a quote. But what kind of data do you need for that? Back to the garden. It's pretty similar to the makeup, but this time there's multiple categories. Like in this case, you both have a lawn and you have a tree. So instead of just having 4 categories, we're going to create a file with the different categories and the image itself. So for each image, we're just going to fill this text file, describing them. It's a lawn, a tree. It's just a bush bed, image, digging, lawn, and that's the data for this particular network. We're going to end up with a folder with a huge amount of images and the text file describing all those images. And this is just a subset that I found on my phone just to try out this model and see how well it would work. And if we're going to train this model as well, we can use the same platform as before. But this time, it's a multi-label classification instead, where you just pick the images, upload them, and then picking the text file which describes all those images. And deciding on a name. OK, so while this one is training, let's look back at the network again to see what it actually will see during this training. So the aim of converting this into discrete categories again, but not just one category this time. This time, I want to go for multiple categories. So we just need to transform this high-dimensional image once again into a lower-dimensional representation of it, just like before, and then into these discrete categories. We're going to use the same type of network and just transform it all the way down to the lower resolution image. Is it a tree? Is it a bush? Yeah. This is how it looks like during the training. You'll see how the image is converted all the way down into this discrete. And we're going to run this until it actually learns. And the training is done again. You can go and see how a network, how it performs when it gets an image. So this is the actual output. This algorithm identified the different parts of the garden and actually wrote this entire quote by itself. So the only thing that's left for me to do is just send this to the customer, and hopefully they will accept it. So that's AI in gardening. And the key takeaway here is that even though it's a very simple algorithm, it's a very simple solution, you can still apply it on a time-consuming and an important problem. OK, but what about AI and furniture? By show of hands, how many here have bought or sold anything on Blocket? Yeah, so you know the procedure. If you're buying something, you have to go through a lot of badly written ads. If you're selling something, you have to write the ad yourself. And I've been selling a lot of stuff, so I found it pretty annoying just reading ads that were not describing the product that they're trying to sell at all. So as before, you just want to have that transaction, you just want to find that piece of furniture or whatever you want to buy. And once again, I thought this could be solvable using AI. So AI could write that ad for you. So looking at selling stuff, what's the most annoying part? It's basically searching for something without any keywords or tags, and you're searching for a green sofa, and you're getting just sofa or couch. And the goal with this, to create an algorithm that would take a picture, transform it into a descriptive ad. Something like this. If you have this couch and you don't want to write the ad, the algorithm will probably say, gul tvåsitsig soffa säljes for you, instead of you doing the job. But for the data in this case, because we don't want to categorize this couch, we want it to be written, we want the algorithm to actually write something for us, to come up with a new ad for it. So it's pretty different, this kind of data set. So what we're going to do in this case, we're going to take a bunch of photos, create a file where we describe every single image. Like in this case, yellow sofa, something we're going to sell it. This blue couch, we're selling this and that. This one is red, it's nice. it's cheap. This one is fresh. It's pretty new. We're moving out, so that you can buy this amazing couch. Maroon. Antique green. So for this data set, I went a bit further, and I created a much bigger set because this algorithm needs to learn how to write in Swedish. It doesn't know it from the start, so it misspells a lot. So we have to have a bigger data set for this one. So I went with 16,000 images and 16,000 rows describing these couches. So let's look at the training of this algorithm. How creative can it get, basically? Same platform, just picking text generation instead, uploading those sofas or pictures of those couches and tables, and then uploading the file describing them as well. Okay, great. Trains. But what about what happens inside of the network? What will the network actually see now that we wanted to write something to learn Swedish from scratch? We wanted to tell you that we wanted to not misspell and have a good grammar, of course. But how does that happen? So we're going to go from high dimension to low dimension again. So the same kind of network, but this time, instead of just having this little top, we're going to add another network to it. It's called LSTM. It's long-term short memory. And we're going to connect it to this convolutional neural network. And what we're going to do, these white spots, it's the vision. It's where the algorithm is looking at the image. It will look at the seating of the couch, and it will write a word, selling. Then it will look at the seating on the back of the couch as well, just looking around, trying to understand what's in this image. And it will say yellow, perhaps. And then it will look at almost the entire picture and say two-seater sofa. So this is how it learns to actually write something and come up with their own ads. But let's look at the model that we trained to see how creative it could get. So I found some pictures of different homes, and I tried them with this model. So this black leather couch, and the algorithm said, fin soffa I äkta skinn. And the interesting part here is that it can actually see the difference between fabrics. And so you can see that it's leather or if it's another fabric. But also just to show you the range. Another couch that I found online. And the algorithm said, vi säljer vår fina och bekväma soffa på grund av flytt. So we're selling our nice and comfortable couch because we're moving. And all of us wondering is, who's we? So this model actually saw the pattern inside of the different ads and actually understood that humans want to tell other humans why they're selling their stuff. So this one came up with they're moving somewhere. And one last for the range of their creativity. Like this home. And the algorithm says, vet egentligen inte varför vi säljer den, men vi skulle förnya och då blir det så här. So in English it's, don't know why we're selling it, but we were renewing, so it just happened. So this is showing how creative it can get out of the data that you're providing to it. So this is not pre-written ads, it's the algorithm look at an image and then writing it for itself. Okay, so that's furniture. And the question for this was, how creative can it get? Depends on the data. Let's look at the very last part, which is AI and cancer. It's a very exciting field. And it's coupled with my background in biotechnology. I spend a lot of time in the lab, in the wet lab, looking at bacteria. And what you get is this kind of images. It's image of human bone cancer cells from a 16-year-old girl. And if you're a researcher, you want to find out how well your drug treatment is working with this kind of images. So one thing is that you want to count them to see how well or how effective your new drug is working, basically. And I worked with a company back in San Francisco, and I saw their struggle. They end up with hundreds of images. And once again, I convinced the researchers that we have to solve this using AI. There's no other way. So that's what I'm doing right now. The research behind this, when you're in the laboratory, you end up with hundreds of images, and they're all low contrast and low resolution, just like this one. And it's just this one, it's hundreds of them every single day, and you don't have time to go through all of them as a researcher. So what I want the model to do, a range of different things, but in this case, we want them to count all the cells for the researcher. It takes them a couple of hours because it's so low resolution, but my models can do it in seconds, so that's the research behind it. And the goal is basically feeding a photo to the model, having the model count all the cancer cells accurately and very fast. So this is the scope, and actually finding them in the picture as well, so not just telling them how many cancer cells there is there, but also pointing them out. The data for this is pretty different compared to the couches or the makeup or the garden pictures. Instead, to find these cancer cells, we have to point them out for the model. We have to create a data set where we're telling exactly where the different cancer cells are and the width and the height of that cell in particular. It's pretty tedious, but you have to do it once to train the model accurately. So this is the data set that's going to be needed to train a model like this for cancer cells. Once again, you end up with a folder with a lot of pictures and a text file with a lot of data where those cancer cells are located. And this is a very, very small data set. It's just 400 images. And I really want to stress this part as well. You don't have to have a huge data set. You can use pre-trained weights like I did in this case, and you will still have a very accurate model. So let's train this one as well and see what we can get. So while it's training, let me just show you what's behind this model again, just to see what the network will actually see while it's training. Instead of categorizing it, it will divide these images into very small bounding boxes. And for each bounding box, it will predict if it's inside one of our own bounding boxes as well. So this algorithm is pretty convoluted, but it works perfectly for this kind of case. And let's see what the training will say about this as well. So as a researcher, you can just log in, upload your cancer images, and in seconds, the algorithm will count them and point them out and tell you how many there are. And in this case, there's 28 of them. So that's a bit about AI in cancer. And you can actually train a model using cats and dogs. That's the weights that I've been using for these cancer cells. It's pretty random, but using weights that's already out there, you can still have a very accurate and well-working model. So just to recap, we talked a bit about makeup, and the key takeaway here is that you can use open data by applying your own expertise and transform that data into something that's going to be useful for you in your case. Then we talked about gardening and AI, and the key takeaway here is that even though it's a very simple application, a very simple solution, you can still solve time-consuming and difficult problems. Furnitures and AI, the key takeaway here, the creativity, it's endless. And the very last part, cancer and AI. You can use pre-existing weights and train a very powerful and accurate model by using cats and dogs. Thank you.
Thank you, Norah. Let's sit down and have a talk.
Yes, sure. Thank you.
Thank you. Wow. I mean, you say you're self-taught.
Yeah.
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 Where did that start? How did you come up with that idea?
In terms of programming,
Yes.
I love to create products. I think that this kind of presentation makes sense in that case. But I love taking something from the idea and to actually a real product or a real solution or a real service. So I always had that. I've been driven to, just convert ideas into stuff.
That was what I was going to ask you as well. What drives you in all this? But it's actually creating something that could be
just taking something that you thought about and just creating something real that people can use. And all of my models are up online and they were used by people. So yeah.
How do you do self-training in AI? If I want to do it when I get back home, yeah.
Like training your model?
No, like starting off, like from the beginning, if I
Oh.
don't really have that much understanding from the beginning.
There's so much so many resources out there. That's one of them that I'm referring to with my GitHub. So there's so much for free, like Fast AI. It's a very basic but very pedagogic, platform that you could use. So there's a lot of resources out there. But that's the one I'm linking to right now as well.
Perfect. Well, you showed us a lot of different work here, different processes that you've been working with. And one question from the audience is, how long does a process take? I guess it depends, like, from where you start measuring, but...
Like training?
Yeah.
In terms of training? It really depends. If you have a small data set like I usually have, it can be run pretty fast, like as fast as I showed you here, like within 5 minutes if you have a very small data set. But if it's huge, like in some cases with the couches or the sofas, yeah, it can run for like a day or 24 hours. But that's something I'm working with the platform, like providing the GPUs, because you need a lot of like data, but also like in terms of power.
Did you start off with the makeup? Was that like the first step for you?
Yeah, it was. I had no prior knowledge, but I really saw this problem with those tutorial videos. So I tried to, without any prior knowledge, I built that very first app with these 3 steps.
How much grit do you need to actually collect all these images?
It depends if you're interested.
Yeah.
It was pretty interesting sitting there just cropping them out. Now I have other tools for that, so it went by much faster. But back then, yeah, a lot of grit, I would say.
Okay, a question about the cancer cells. With what accuracy can your AI algorithm detect the cancer cells?
In terms of the object detection, I have different models. If you want to like evaluate the size, if they're dead, if you're dividing, that's other kind of models for. But just detecting them like this in bright field images, those very low resolution images, it's like 99.99. So it's super accurate for the object detection ones.
Wow. And the question that's quite similar to that one is, how do you know when the data set is good enough that you can rely, that it's to make it reliable and give you the desired results later?
I have different like processes where my platform trains the model different networks, like different depths. So starting with a small network and then moving to a bigger one, and altering the training, the length, basically. So I'm doing a lot of tests and also looking at the accuracy, looking at the validation. So I'm comparing a lot and drawing graphs just to know where to stop.
You have a startup company. Yeah. What's special about being a startup? What do you have to sort of share from that perspective to the people here today?
Oh, wow. It's a lot of work, but it's so rewarding. Everything you do will just take you further. So it's super rewarding, I would say. And you build something from the ground up, and it's all yours. And you will see, like, yeah, it's super rewarding, I would say, just to, summarize it.
What is it like both products and services that your company...
In my case?
Yeah.
It's the platform.
It's the platform.
Services. Yeah. It's the deep learning algorithms that I'm training for different kind of researchers or different, basically products as well. It's not just researchers, but it's mostly researchers and mostly cancer cells and stem cells and some heart muscle cells, as well as Daniel mentioned.
And how much have you been dependent on like the co-creation that we've been talking about a lot today? How has that been important to you?
It's a very important part. The open source sharing, I try to share as much as I can. Not all the code, of course, but it's a very important part, definitely. And I'm a huge fan of the open source community, and I try to give back all the time.
Great. I think we're in different areas talking about the open source and the open data and the need for platforms to actually help us in doing this as well.
Yeah, definitely.
When it comes to co-creation, the ecosystem is very important here today. It's kind of an ecosystem actually gathering together. And as this conference is a collaboration, you have chosen to move into a world-known ecosystem of innovation and entrepreneurship. When did you do that, and explain that step, and how important is that for you as a startup?
Like moving into like having my own company?
Like you left Sweden.
Oh, right. We always dreamt about having a company in Silicon Valley like everyone else, I guess. So we just took the step to try it out. And the environment there is amazing, all the investors and a lot of like meetups and the whole, everyone you meet has a startup or has something they want to pitch you. So it's a very, very good environment in terms of having your own startup over there.
Because you're in Silicon Valley and New York most of the time.
Yeah, altering in between, but mostly SF, I mean San Francisco and Bay Area.
Well, you have a platform, and the same question as I asked earlier, the thing about like the business models, because in the end it's a lot of hard work and we need money. And I think that's a challenging step for many of the innovations that we have. When are we actually able to get the money back from all the hard work? How do you view upon like business models and when it comes to the kind of platform that you have created?
Yeah, that's an important part. It's built on a subscription model, so the researchers are just subscribing to the different models, and I'm training models as I go along, so different researchers can just hook on it as soon as they have a new cancer deep learning model. So, but basically subscription-based, and it works well. I mean, in that field, it's very fast-moving.
The future is difficult to predict, but when you think about AI, you have a question here from the audience. Do you think your AI algorithm will substitute a medical doctor observation in the future?
Not my particular algorithms, no, but in general, yes, definitely. Mine are very early stage, but those that are out there, competing with the doctors right now, I would definitely say that it will be like replaced. Or at least, definitely.
Another question, which is more a detailed one. How do you know how many numbers of photos you need for each model?
Yeah, you can, it depends. If you're going to use like a pre-trained weights, like I usually do when the data sets are so small, then you could go with everything from, it really depends on what you're training. If you're training something that's included in those trained weights, then you can have a very, very small data set. But it's all about like plotting how well the training is actually moving forward, I would say, how the accuracy changes. But you can start with a very, very small data set. I mean, like in this case, like 100 images is enough to get an accuracy that's good enough for the application, but it really depends on what you're training.
When it comes to the development of AI, you make it really sort of clear and simple somehow, and very useful in different kinds of areas. But what are the main obstacles for it to actually happen and to accelerate, and for us to use the possibilities that it actually gives us?
You mean AI in general?
Yeah, in general, yeah.
Oh, challenges. I think it depends on the application, of course, but sometimes you have to have a high, the accuracy that's needed, it's difficult to reach. That's why I'm very low, early stage research projects, but I will say it's difficult.
Yeah.
It's combined. I think it's both data, but also networks. Yeah. We've come so far, in terms of like self-driving cars and like smart assistants, so it's difficult.
Yeah. The monokeros, is that how you say? Yes. Is it available for everyone, or?
I'm launching a beta pretty soon, so when it's done, the platform is there, everything I showed you is working, but I'm still working with a smaller group. It's not the platform that my researchers are using, because that's highly specialized on cells. This one is more like general. Everyone can train a model on it, but basically it's launching very, very soon.
Transformation, how much is what you're doing actually like a transformation? Or is it just, well, this is very simple, it's nothing special, or is it really like a complete transformation in how we are doing things in our community?
I think on a low level, yeah, definitely. The researchers that I'm meeting with, they're spending hours every day just like looking at images. It's unbelievable, actually, that someone that's highly trained or went to have a PhD actually just looks at images like every single day or just counting cells by hand. So in their case, they can spend like an hour a week just manually evaluating the pictures that I'm predicting. So in their case, it's definitely transformative, and they don't even think about the possibility to actually not doing it for hours every day. Yeah. So in that case, yes. But for makeup, maybe not.
Maybe not. We also have one more of a personal question to you. Have you faced any challenging? Has it been challenging for you to convince investors as a female researcher? Has it been a difference? Do you think? Being a woman in this?
That's a good question. I think in general, yes, but those investors that I met were amazing. So for me personally, no, but I know it's difficult. I know women are receiving a small amount of money, like in general, when you're raising money. But in my personal experience, no.
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 Do you get any sort of ethical obstacles or questions working with this?
If I'm getting
questions?
No, not really me, like personally, since I'm in the lab, but I'm not responsible of the research. But with the stem cells that we're working with, I know there's a lot of question about them, but we're mostly working with doctors that want to cure like super rare diseases. So they're taking stem cells from people that they want to cure. So they're taking some like skin cells and then they're tracing them back to stem cells. So. But not me personally, but the researchers, yes.
Yeah,
they do.
I mean, when you showed the example from the quote, like the gardening, you sounded like really happy that you didn't have to do that work.
Yeah,
yeah. the AI could do that for you. But that's also a fear in society that will AI take our jobs. Do you have to answer up to that as well, or do you feel that no, it just makes life better?
No, it makes life better. I'm happy for an AI to take that off my work, like doing the quotes or like looking for answers. No, I'm happy for them to just take those parts.
Yeah,
but it really depends. I mean, if you're a driver, and then yeah, you might get intimidated by self-driving cars because they're pretty much coming along right now. But in general, no. We should just be happy to leave those tedious work to AI and deep learning.
I think there's one more question here that we haven't answered. How far away would you say we are from replacing radiologists with AI?
I'm afraid to say this because I'm working with radiologists, but it depends on early stage. They're pretty much like replaced, but meaning the human interaction and for people with actual diseases, you still need a human in the loop. But for early stage like research, no.
Where did you want to be in like 10 or 20 years from now?
Wow, that's so long. In terms of the company, I hope to make a bigger impact, to reach a lot more researchers, train a lot more models, but also I would love to like expand this kind of networks. I want everyone to be able to train a model like within something that interests them. So yeah, something within deep learning and a lot of algorithms, I would say.
Yes. I know you're also staying for the evening and you love stand-up comedians, so you're looking forward to that.
I'm staying at the hotel, so I'm going to be here all night.
Yes, so you guys know, remember the ones that were here in the morning, they got a challenge from me because this is like the co-creation theme. And to be able to co-create, you need to have a lot of contacts, right?
Yeah.
So they should collect like 5 to 10 new contacts today. This could be an alternative, and also explain to Norah why you should be on her list, because you might need one of you in the future as well.
Totally.
Because who knows what kind kind of challenges or possibilities that you will take on when it comes to your company. This is really exciting.
Thank you so much. I
Thank you
appreciate
much.
it.
I will give you a present here, and I will explain it a bit more in detail what this actually includes. As you are not so often in Sweden, I think this will make you happy. There are some. This is all locally produced.
Wait, what is it?
And this is like gingerbread.
Oh, yeah, I love
yeah, you like that one?
Yeah, totally.
Perhaps you don't find it as much in not the
Not
Swedish
the real ones.
not the Sundsvall ones.
Yeah, exactly.
Anyways, glühwein, alltså glögg.
Glögg.
Yeah,
Älskar glögg.
yeah, that's nice. And some chocolate, and like the packaging is designed by the Mid Sweden University. So
Thank you so much. I really appreciate it.
thank you so much for
Thank you
attending.
having me.
Thank you.
Thank you.
Wow, we have been having a great day here. We started off early. It's nice to see you all here, and big thank you to wonderful keynote speakers that we had here today. And also all the different people that have been engaged in the parallel sessions has done a great work. I also want to say thank you to all the partners, organizers of this day, and the sponsors, and to all of you who attended this day. Now, we will enjoy a wonderful evening together. We will be about 400 people, so I'm going to give you the details how to do this, so you won't get too crowded. We are not in a hurry when it comes to the program. When you all are settled and you have taken your food and everything, we will have some people talk, and then Elin will get started. But you don't need to rush or to hurry. We will have time for everything. When you go there, you should pass the reception and go upstairs. The ones that were here earlier today, it's where we had lunch. That's where we will meet. And it will be a buffet inspired by autumn. So it's like a harvest buffet, really, really nice. And as I said, we are also really much looking forward to stand up Elin as well, who will join us tonight. Some of you we will meet tomorrow morning, so we'll be back here. Good Tech Conference is starting tomorrow morning. But the rest of you, I really, really hope we will see you here next year. And I would like to leave you with a quote in the sort of spirit of co-creation. It's Simon Sinek who has said this one. We achieve more when we chase the dream instead of competition. So use that when you go on transforming today and the future together and co-create, and have a beautiful evening. Thank you so much.